Okay, so let us wait for another about 4 minutes for other participants to join in this live link. Okay, our speaker has joined, I see. Jimmy, can you hear us clearly?
Yep, I can hear you guys.
Great. So do you want to test if you can share your screen?
Yep, let me do that.
Do you see the sharing link below?
Yes. 1 second. Should be able to share that. Oh. Hmm. 1 second, let me adjust the program on my side a little bit. All right. Can you guys see
Yep.
my screen?
Yes. Now we can see your screen, the opening slide. Great.
Okay, great.
So we'll start in 2 more minutes.
All right, that works for me. And after talk, is there a Q&A session?
Yes, in fact, there might be some questions on the chat box during the talk, and after your presentation is over, the participants can ask questions. Okay.
Sure. All right. So I'll try my best to monitor the chat box. And also, if you guys see there's some burning questions, also please let me know.
Definitely.
Great. Hmm.
Okay. So, good morning, everyone. And I think good evening, Jimmy, because it might be your night time there.
Yep.
And so we are very fortunate to have Dr. Jimmy Ba. He's a prominent figure in the field of deep learning, known for his very fundamental contributions to the development of learning algorithms for deep neural networks. He is actually credited for co-developing the Adam optimizer along with Deirdre Kingma, who was a speaker for WSDL 2023 edition. And those of you who work a little bit on deep neural networks, you must know Adam is one of the best known optimization techniques for training deep neural networks. And Dr. Ba completed his undergraduate, master's, and PhD degrees at the University of Toronto, studying under the guidance of extremely well-known and esteemed researchers like Geoffrey Hinton, Brendan Frey, and Ruslan Salakudinov. Incidentally, Professor Hinton was the inaugural speaker for Winter School to 2023 edition, and we just had Ruslan's session in this year's Winter School few days back. Notably, Jimmy was the second ever student from Canadian institution to receive the prestigious Facebook PhD fellowship. In 2015, his team achieved the highest ranking among academic labs in the image caption generation competition at CVPR. He is also one of the co-developers of layer normalization techniques that I believe many of you already know. So with this brief introduction, let us hand over the stage to Dr. Jimmy Ba and listen to his excellent lecture. So Jimmy, the stage is now all yours. Thank you very much.
All right. Yeah. Thank you so much for the introduction. I'm very flattered, and it's great to see my academic lineage have some showing in your conference. Great. So I'll try to, you know, pass on the baton, and hopefully this will be an entertaining talk for all of you. So the talk today is going to be on large language models. I think because I cannot see the actual audience here, so if you have any questions, please drop them in the chat, and I'll try my best to monitor it. All right, so currently I'm at XAI. So a lot of the materials in this talk is actually done by my student at University of Toronto, and all the research would not be possible with these beautiful people in my group. So just give them a shout out to Harris, Karen, Yongchao, Michael, and Silvio. All right, so I think ever since November 2022, right? End of November, December, during the New Year's time, the ChatGPT has taken over the world by storm. And around the same time, we start to see many internet scale generative models, right? Starting with the GPT model, GPT-3, that is the predecessor of ChatGPT. Some of you who played around with those models back in the days in the year of 2022 will probably remember this interface. That's called OpenAI Playground, right? So what you can do is you can actually type in a particular sentence, in this case, write a poem about Japan, and the model will just actually complete the task for you in the following sentence. And a year, almost 2 years ago, right? These systems are pretty primitive. You can just start a single round of conversation and requires a lot of prompting. And within the last year and a half, we have made significant progress in terms of prompting these models to do multi-turn conversations, to solve mathematical reasoning problem. And nowadays, these models can be utilized as assistant to do automated research. And at the same time, we have those image generation models from Stable Diffusions, right? So going beyond the text modality. So instead of generating a poem for Japan, now we can actually generate an image of Jesus Christ play with an iPad. So immediately we see a lot of images that's very creative that spread around the whole internet. And many of that thanks to a essentially an internet scale generative model trained on billions of images. And beyond both writing poem, writing essays, and generating natural images, these internet scale models is also able to solve many competition tasks, many competitive coding tasks. So this is a screenshot from the first generation AlphaCode. And although it's actually quite costly to generate a particular solution, um, for example, the model has to generate millions of solutions and filter them down eventually. But one of those solutions, if you can verify, is actually able to solve many of the very challenging programming tasks. So what's in common between all those internet scale models? Well, I think all of them is trying to learn this representation of the world. And we can learn them simply just by collecting billions of images and text data and spend a lot of compute and train a very large model. And eventually, it seems this program is just going to continue. So if we plot that in this 2D axis, the x-axis means time. So, and the y-axis is the performance of the system. So I'm showing two curves here. The first curve that takes off very quickly around 1970s and kind of plateaus. You can think of these as the traditional AI system or classical AI system, where majority of the decisions are made through a rule-based system. So they worked really well in the late 70s and early 80s, and eventually empowering systems like IBM Watson. But over time, these systems becomes harder and harder to scale up because the rule-based system just got more and more complex as more engineers work on this problem. Everyone's introducing rules and decision breaking points, and very quickly the system get very clumsy, very complex, and hard to maintain. So the performance of the system becomes very difficult to scale, even with pile an army of engineers to this problem. In contrary, we see the second curve that started to take off around early 2000s. So this curve kind of denotes the deep learning revolution we're seeing today. Most of the techniques we're applying today has been ready in the 70s in terms of the exact architectures of two-layer perceptron, and 80s, the backpropagation learning algorithm for these systems. And then with the boom of the internet, all of a sudden we're able to collect millions, if not billions of training examples. And paired with the increase of the semiconductor advances, allows us to build faster chips. Those two forces allows us to train neural networks at an unprecedented scale since the early 2000s. And people start to take notice of this trend around 2012, when there's a model called AlexNet that started showing up. So many of us has been in the field for a while, studying deep learning. We may actually start to make the conclusion, well, we have seen this takeoff before in the early 70s and 80s. These systems may work really well now, but maybe after a few years, they will become very hard to scale because infrastructure challenges become very hard to collect even more training examples. So the current scaling is ending, right? So maybe the deep learning revolution is also going to taper off in the next couple of years. So here's a question. Is this time different? Is it possible that we're pretty far away from the current generation of technology to, taper off, or in other words, we may see another 10 or 20 years of, improvement in our current deep learning systems like ChatGPT and reach much higher heights. So in order to answer this question of the future prediction, this talks about, maybe we can take a look in the history that will help us to answer this question. So how do we answer this question, and where's the future going? Well, let's think about what happened the last time. Let's think about what was the last time as a whole in the society of machine learning, there's a huge excitement and large breakthrough. As far as I can remember, I joined the grad school around 2012. And that was a time where the AlexNet or the ImageNet challenge, the supervision team that was done by Alex Jasky, Elias Sutskever, and my previous advisor, Jerry Hinton, that really took the first spot of the competition on year 2012. And very soon afterwards, the technique that developed that essentially utilized a convolution neural networks was previously developed by Yann LeCun in the 90s and just simply scaled up from 3 layers to 5 layers. And instead of running on the CPUs, now we run on 2 GPUs. Instead of training on 50,000 MNIST training examples, now we're training on 1.2 million ImageNet images. The system with the same algorithm, like backpropagation and stochastic gradient descent, is now able to perform much better than the previous generation of human handcrafted computer vision pipeline. And 3 years after the release of AlexNet, the whole field has been making consistent innovations by making the model deeper, introducing batch normalization, inventing the skip connections in the ResNet that just continue to push up the benchmark numbers and almost reaching superhuman performance in recognizing thousands of different image objects. So imagine if you were in a company around 2012 and some of your researchers invented this technique that's now all of a sudden enable the computers to see the world and be able to recognize objects. What would you do with it? Or in other words, if back then the AlexNet was open sourced, including all its weights and infrastructure, how can we possibly utilize AlexNet to solve a new task? Well, the answer is pretty simple retrospectively. It's called fine-tuning. So what typically has been done in the last 10 years is that we take a pre-trained ImageNet model, we cut off the last layer, and introduce a randomly initialized softmax layer on an entirely new task. We have seen millions of papers in the last 10 years published on this topic. So this is one single example that you take the original ImageNet recognition model that trained to recognize thousands of objects. Now you can repurpose the network by training the last layer, training a new softmax last layer on a new training example that contains different people arts. Now all of a sudden, your model is able to deploy it in art gallery or in places to sort out a lot of the Kijiji and eBay objects. So if we characterize like what we can do with these models, you can kind of think of them as if there's a very strong pre-trained model at the beginning of the deep learning boom, namely those ImageNet model, it's quite easy to repurpose those ImageNet model to a new task if we can go out and collect a lot of demonstrations. That is, a lot of image and label pairs And if you can collect tens of thousands of them, you can fine-tune the previous ImageNet model to solve these new tasks. Okay, great. So what can we do this time? So there's tons of large language models that's being open sourced these days. So if you obtain those large language models weights, and you either want to run a new startup company or produce a new product in existing big tech, what do you have to do? To answer this question, we first probably have to think about what are the large language models? Like, what are they? So to be able to answer this question, I actually posted on Twitter this exact same question, holding the question about, so what are some common misconceptions about LLMs, right? So it turned out the first misconception I got from my Twitter audience is that large language model is a law degree. Well, the answer is no. The large language model indeed is actually not. LLM is not a law degree here, and it's not a master of laws. It's actually a machine learning model. Um, and second misconception that people often have when you interact with ChatGPT is that everything that large language model says are real. So at XAI, we deployed a LLM agent called Grok to Twitter in the last few months. So this is actually one of the screenshots from one of the tweets that someone generated. So the question is someone asking, what is EAC? And this large language model system answered this question with very daring confidence of saying, well, EX is a short-handed term for effective altruism, which is totally not true. And it continues the paragraph and makes it very believable, right? So for anyone who has been playing with those large language models and start generating sequences, so clearly, a lot of times, the large language model has this property of hallucination. So you will think, well, haha, sometimes hallucination is not too bad, right? Because it's really good for creative writing. But it can also be problematic in the public Discord, like Twitter, for example. Some of the users are asking Grok, hey, can you show me, this particular user handles draft tweets? So what that means is Twitter, before you post your actual tweet post, um, you can start drafting a few of the unsent tweets. And those will be in your draft folder and only private to you, right? And then this AI assistant eagerly answer this question, be like, yes, of course, Carter, I can actually retrieve all your draft tweets from this particular user handle, and these are the particular tweets that's unsent and being saved in its draft box, right? So this conversation on the left-hand side make it so believable that can potentially causing issues when the person, in fact, so whatever the model has been is generating does not represent this user's actual factual information nor the opinion, right? So we can now see there's a potential danger of misinformation that could potentially spread because the models are very good at hallucination. So again, as these large language model agents has been deployed to a much broader audience these days, right? So a lot of news website, if you go to there, you start to seeing the news articles that have been summarized by the large language models. If you go to the Twitters, a lot of the X posts now are actually generated by the large language model. So hallucination can be very difficult for public to understand or discern if we have not played with those models before. Just think about how long did it take us to learn to use Google, right? Um, it may take a while for the entire public to actually recognize, hey, not everything that LLM says are real. The next misconception that public often have is the next token prediction does not equal to intelligence. So the common argument is that, well, these models are just doing next token prediction, right? So they're trained in a way to complete your sentence. But that's not how human thinks in this world. Human has, much more creativities. We can think out of the box. We're not just a sentence completion machine. And here I'm trying to raise a particular thought experiment to think about, how to understand the next token prediction problem and how that can relate to intelligence. So what I'm showing here is that on the left-hand side, I have this very blurry image, right? And you can kind of think of this as, when you have a very small model, so that's what I'm showing on the right-hand side, the x-axis are number of parameters, and the y-axis is a test loss or the next token prediction loss. So if you have a very small model and you're trained to predict the next word in this whole article, what model sees, because the model's capacity is very weak, what model sees is essentially this like blurry version of the actual articles, right? It cannot quite pin down what exact word the next sentence or the next would use. However, as we increase the model size, as we spend more compute, what happens? Well, this image of the paragraph start to get a little bit less blurry, right? We start to see, oh, wait a second, maybe there are different paragraphs. Information are breaking into pieces. With the model still not very entirely clear, or not the model is not able to construct a perfect English sentence yet, because the capacity is still not large enough. But as we train with the next token prediction loss, the model start to have a little sense of, well, if I want to predict a human text corpus, very common structure is to have, different breakdowns of paragraphs. Now, again, as we increase the model capacity again by spending more compute and overall, well, things to start becoming even less blurry. We start seeing, hey, there's punctuations, there's separations between the tokens within a paragraph, right? So not only this blob of text is being broken into 3 paragraphs, even within each of the paragraphs, there are spacings, and between the spaces, there are words. And as we start to, increase model further, things becomes more and more clear. You start to see, hey, actually, the model start to learn the grammars and the syntax of the underlying language. Okay, so now increase the model even further. What happens is that, well, you start to able to see that the model is able to start to predict those words better and better. So now you start to learn the concept of, oh, they're names. They're different English words that's being arranged to mean certain things. And once the model is able to predict each of the individual words really, really well, then you scale the model further. In this case, the models actually start to gonna learn the long-term correlations between the words, right? And those are the actual plots, the meanings of the stories. So here's this very simple argument to say that although the next token prediction task is very simple, but as we're spending more and more compute, as we make the model larger and larger, the large language model themselves eventually will have a chance to learn the underlying meanings behind the sentence. Namely, the model will become more intelligent, right? So the argument here is that, well, the next token prediction is kind of like intelligence, but not quite like human intelligence, right? For human, most of the time when we read a book, we start to learn the underlying meanings behind the sentence first before we master or perfect our writing skill, right? But for language models, it learns to perfect its writing skills and its English grammar first before learning the underlying meaning. So the next token prediction, through this thought experiment, may actually have a chance to produce intelligence, but that they're more alien-like because it learns the syntax first before learning the meaning. All right, so the next misconception from my Twitter threads is that the larger the model, the better they are. So in practice, what we see is that in the last 5 years, ever since the dawn of the first generative pre-trained transformer, aka GPT, released by OpenAI, every year the model is being 10x in the number of parameters, almost. So everyone's rushing towards training larger and larger models. And then we can also see that, at the same time, Jerry Kaplan and others from OpenAI at the time, not Anthropic, published a paper on neural scaling law, where showing that as the number of parameters increases and the number of data sets increases, the next token prediction loss gets lower and lower, right? So a natural conclusion from this is that, well, if the models are larger, they ought to be better. But is this always true? So if we plot the performance of a lot of the large language model that's being released in the last a year and a half, in this plot, where the x-axis is number of parameters, and y-axis is the performance on this evaluation benchmark called MMLU, developed by Dan Hendricks. We start to see that there's no clear trend, actually, in terms of the model performance and the number of parameters. In fact, if we look at the data points on the model has highest performance, they're actually in the middle of the road in terms of number of parameters. For example, Llama 2 is around, well, it's giving the performance around 60, 68, 67% on this benchmark. So what's going on here? So it seems like the larger model is not doing better, right? So let's change the perspective again. Instead of plotting these dots in terms of the number of parameters, we can plot them in terms of number of training compute they spend, the training flops. So how do we calculate training flops for large language models? Well, we just take the number of training examples or the number of training tokens, multiply by the number of parameters in the model and times 6. That's a very crude approximation. Then we obtain the actual training flops. Now we start to see a trend here. The model overall has less training flops, perform worse. And overall, the model spending more compute in training, regardless its size, oftentimes does better on this benchmark. So the conclusion over here is essentially that the more parameters does not always equal to better, but instead we should think in terms of flops are actually more indicative of the performance of the model. So more flops actually indeed equal better performance. So this is almost independent of the number of parameters. So next time when you go on Twitter or go on, read research papers where, there are comparisons comparing models in terms of size, maybe think twice. What's really important is how much compute they spend in a model. A large model with very little compute invested and oftentimes perform suboptimally compared to a medium-sized model with a lot more compute. For example, the Llama 2 model. The fifth missing conception from the Twitter post is that the capabilities seems always go up with compute, right? And that also confirmed by my previous slide. It does seems like as we chart the x-axis and the number of training flops or more training compute, the more the merrier, right? The more compute we invest, the higher the benchmark performance we get. So is this always true? So this is a competition called inverse scaling law, and was um, was running in the last a year and a half, essentially asking the question, for most of the tasks, for most of the benchmarks, as the model size increases, the performance on the benchmark, on the task also increases. So is it possible that there are tasks, as the model size increases, the performance decrease? Is that possible? And what do those tasks look like? So it turned out two of the students at U Toronto 2 years ago, Sheldon and David, what they found is that indeed there are actually tasks. As the language model scales up, as the models are better at predicting the next token, as the model gaining more intelligence, the performance actually decreases. The key intuition here is that because the large language models are trained to predict the next word in a sentence, fundamentally, they're trained to imitate the human writing. And now, as the language model becomes larger, they become better at imitating humans. So maybe they also tend to imitate the logical fallacies in the human writings as well. So here's a quick puzzle. So consider the following statement. If John has a pet, then John has a dog. If John doesn't have a dog, so both statements, let's consider both statements. So what can we conclude from the statement one and statement two? Well, so here's one of the options. The conclusion is that therefore John doesn't have a pet. So now is this conclusion correct? So we can just feed this exact question as a prompt into a large language model. So what should be the answer? Well, in order to understand what's going on here, say, well, the answer is actually yes, right, to the original question. John does not have a pet is the correct conclusion. But sometimes some of us may think otherwise. So this is called the modus tollens. It's a form of the logic and deductive reasoning process. It essentially takes the form of statement P, then the statement Q is true. If then you're given the statement Q is not true, therefore the statement P is also not true. And sometimes this form of logical deduction is quite hard for human. Then what happens if we evaluate this sort of logical deduction on large language models. So this is what Sheldon and David did. So if we plot, if we generate a lot of these puzzles and plot the performance of the large language model on these puzzles as a function of number of parameters, what happened here is that as the number of parameters increases, for example, as we start using from very small 7 billion, a few million parameters to billions of parameters with more state-of-art models from Anthropic, from OpenAI, the GPT-2s and GPT-3s, the performance actually decreases with the number of parameters, right? So it does seem like sometimes if the model imitates humans too much, then they're gonna start to make the same logical fallacies as all of us. All right, so that's enough of a detour to understand or to get some intuition about the large language models. So now we're back to the same original question, just like in the ImageNet era. So now if you're given an open source large language model, what can you do with it? How do we repurpose a model to a new task? Well, the first answer should be pretty obvious and collect a lot of training examples, a lot of demonstrations from human on solving a new task. For example, translation task or mathematical reasoning task. And then we can fine-tune these models on this new example. So what else can we do? Well, turned out that few-shot prompting is one of the staple capabilities for a lot of these language models, right? So this is one example for the chain of thought prompting. So what I'm showing here is that in order for the model to answer this simple mathematical question, like an elementary school math problem, for example, so the real question here is that the cafeteria had 23 apples, and if they used 20 to make lunch and bought 6 more, how many apples do they have? Instead of directly getting the model to answer this particular question, we can actually prompt the large language models with an example of how to answer these in the style that we desire. So in the chain of thoughts prompting technique from the techniques, they show that, well, the performance of how well we can answer these elementary school math problems is highly dependent on what example we show in the prompt. So now instead of just showing a simple correct answer, we can actually show a demonstration where the human will start a few reasoning steps. For example, the Roger started with 5 balls, the 2 cans of 3 tennis balls each is in total 6 tennis balls, and therefore the number is 5 plus 6 equal to 11. So now if we show these few short examples to the model, on the real test example of the cafeteria apples, the model is going to imitate the previous chain of thought or the answer format in the future prompting is actually, provide a more thorough reasoning steps and in the end reach the correct conclusion. So the few-shot prompting techniques is quite unique to the large language models in the sense that in the previous generation, when we had the ImageNet model, it's really hard for us to introduce a few short examples for the model to follow, right? Inputs are images and outputs are the labels. It's almost impossible to steer the model to answer, to spend a bit more compute to think about the solution more thoroughly before outputting a particular label. In the ImageNet era, in the convolutional neural network era, every single image is going through a fixed number of convolution layers, and in the end, reach the solution. But with chain of thoughts prompting, the model may dynamically allocate a number of tokens to solve different tasks of different difficulty. So this is a very powerful technique that in the previous generation, in the ImageNet classifier generation, we do not obtain. It's not so easy for us to make the model smarter just by simply prompting. And in fact, instead of showing the model examples, we can actually just directly ask the model, well, in order to solve these simple elementary school math problem, no example shown. Just say, hey, what do you think? Can you think step by step before you give out a final answer? And these are the zero-shot prompting techniques that just by changing how we word the question a little bit, the model all of a sudden is able to produce an answer that's more accurate and more thorough than before. So coming back, instead of just doing, fine-tuning, like how we fine-tune the ImageNet model, with large language models, we can actually go out and collect one or two very high quality training example and show them in context, and the models are able to adapt and carry out the new calculation. So this is a huge difference between the previous paradigm, because in order to fine-tune an ImageNet model, oftentimes you need tens of thousands of images with very high quality human label. But you only need maybe two examples. And any one of us can sit down and write down those demonstrations and hope the models are able to carry out and follow exactly what we do in these few-shot prompting techniques. With zero-shot prompting, we can even just describe the task with words. We don't even need to generate demonstrations. We don't even have to carry out the calculations. So these are very powerful techniques that all of a sudden allow everyone to contribute using higher quality answers, just simply through prompt engineering. One of my very favorite Twitter posts in the last 2 years was from Phil, who's a professor at MIT. And so Phil notice that if you have those like internet scale generative model, especially the generative model has a text capability, it's quite easy to prompt the model to start, answering the question, hey, if I want to generate a very beautiful painting of the mountain next to waterfall, what does that look like? So this is what the model generated with the first image. And as we, introduce modified prompts a little bit by saying, hey, what happens if, the painting is very beautiful, right? This is the second image it generates. So now generate a very, very beautiful painting of a mountain next to waterfall. And then you can raise the vary to the power of n. And in the end, the model is actually going to generate, better and better looking, and in the end, a bit more abstract paintings of waterfall. So this is quite interesting because even for a task that we know how to solve and you can describe it with one sentence, we can actually start modifying those prompts such that the model's performance will increase just by simply changing the words and changing the prompt structure. So some of the students in my research group noticed this property that, hey, is it possible that if we can get the model to output the instruction of what's doing, and then the human comes in to modify the instruction a little bit, then you generate data from this modified instruction. Is it possible to form this feedback loop that every time the model proposes some instructions and human improved it a little bit, and next time the performance of the model gets better, and then you ask the model to generate some instruction again, and the human come in and modify it. Is it possible to form this self improving just by utilizing language models and no training, gradient descent training. So to get a intuitive understanding of whether this is possible, imagine the following. So this is a warm-up exercise. So you're given a data set. On the left-hand side, you have a set of sentence pairs. For example, in the first example, you have the child hurts their knees for sentence 1 and the child starts crying, sentence 2. And the output, the desired output here is that the child hurt their knee, right? So it corresponds to sentence 1. And then you have other examples. It seems like the relationship between input and output is that the output is always choosing one of the sentences. And perhaps one of those sentences is the cause versus the effect of the two events, right? For example, the storm happened first and therefore the school was canceled. And then the model need to output the storm, right? Similarly, the boy threw a rock and therefore the window broke, right? So it seems like there's a causal relationship here, and we're asking a model to output the cause between the two pairs. So now if we want to ask the large language models or GPT models that consume this data set and describe what task this is, how do we do it? Well, so what we can do, a few task description, right? So these are the 5 examples that generated by the model. You can say, well, each of the input consists of 2 sentences, and where one is the cause, the other one is the outcome, right? And write a cause sentence. And you can formulate as the input is the cause and effect, and write a cause. So what you can do actually is you can propose a few of these sentences and ask the model, hey, given these tasks and given the inputs, what should be the output in this example? We can actually measure the task accuracy for all these different prompts. The prompts that gives the highest accuracy may not align with how human thinks about these problems. The model is given the prompts of the inputs of cause and effect and write the cause, a much shorter sentence paired with the input of the data set actually give you the highest test accuracy. So this is very interesting, right? So previously we always think that, hey, if you want to do prompt engineering, we should spend some human compute or having the grad students sit there, think really hard about it, and come with some killer prompts. But now, maybe the human intuition of what prompts works best may not always be true. So is it possible for the model to automatically invent its own prompt and modify it to improve the task performance? So this is the whole point of this work called automated prompt engineer, right? Because if you want to get the humans to invent those prompts, it's very time consuming and very unintuitive which one will even work the best. So instead, we formulate the problem as, hey, we can take a set of the input, feed into a large language model, that's an automatic prompt engineering, and then give you the actual output of what the task is about. And then we ask the model to make many proposals, and we rank them by the final test performance. So in this case, you almost think about the prompts is the program the large language model has to generate. And if this program describes the task really well, then the model's performance on the actual test set should be very high, right? So we can utilize this as a training signal to modify or gradually improve our prompts. So this is very similar to AlphaCode. where in AlphaCode, we ask the models to generate many different solutions for a coding problem. And then we filter them and evaluate them. In the end, we obtain the best solution. So instead of doing the code program, we ask the model, hey, can you generate a lot of natural language instructions that describe the behavior that we want, right? We show the demonstrations, we show the input and output pairs, and we ask the language model to actually rank all these generating instructions, we filter them, and eventually pick the best instructions to execute that in fact gives the highest performance on the given task. So the prompts we use for the model to actually generate, the actual examples is the following, right? So I gave a friend an instruction, 5 inputs, and the friend reads the instruction or wrote down the output, and here's output, and ask the model to guess the instruction. So if we do this, the model will come with a set of proposals, we rank them, and that's the inference phase of the whole automated prompt engineering. Instead of doing this very simple prompt structure, we can also try to get a model to do infilling. So that is, well, if the model can actually, decide which prompts to which the corresponding instructions, we can rank them. And then after we rank them, we can score it using the actual test set by using a large language model. And then once we pick the highest performing prompts to describe the particular task, we can ask the model, hey, can you mutate it? Can you rewrite this particular instruction such that the performance of the task can be better? And we call this the resampling phase. So after resampling, the model actually can modify its previous generated prompts and to continue improve the score. So effectively, we can actually leverage the instruction following capability of the large language models to iteratively improve both this task description, aka the instruction of the task, and now given those additional instruction, the model's performance on these language understanding tasks can be improved just by running a lot of inference steps between first infer the instruction, pick the best instruction through the scores, and then we're going to rewrite the best instructions to continue hill climb on the test scores. So let's look at how well this system works. So we tried it on the 24 instruction induction tasks, and comparing to the best human performance, which is the blue bar, the automated prompt engineering, that is, make an initial guess of the instruction, and then continue the rewrite loops to iteratively improve the instruction on a particular training set, can almost always do better than the best human prompts for this data set. And this is just an example of showing that maybe the best human instruction may not necessarily be the best instruction that will give you the highest performance when prompting a language model. Why is that? Because, well, large language model, although they're trained to imitate human, the best performing prompts might be very unintuitive. Right. So we also perform this on a much more challenging big bench task that beyond just guessing the causalities and finding out the acronyms. And on the big bench tasks, the automatic prompt engineering or APE achieved human level performance on 17 out of 21 tasks with no human input on how to prompt this system. Many of you have seen this, let's think step-by-step prompts, right? That's zero-shot prompts that give you very high performance on some grade school math problem. So instead, when we apply the automatic prompt engineering to this problem, the ape to this problem, what we do is we start with a set of questions and answering with reasoning steps using the step-by-step prompt. And then we purge the training examples that has incorrect answers manually. Then we build the training set using the step 1 and step 2. Then we apply ape to essentially optimize the prompt. The prompt here is that, well, instead of think step by step, maybe the model can say, let's think like a detective, or let's be realistic and think step by step. Turned out, if we iteratively improve the prompts here, we can get additional 5% improvement over the think step by step prompt. And what the model discovers is that let's work this out in a step-by-step way to be sure that we have the right answer. This sentence is totally unintuitive and will be very difficult to imagine a human or grad student is able to discover this particular prompt to give you the highest performance on the task. Right, I'm gonna quickly skip these 2 slides. So what's the key takeaway here? So the key takeaway here is to think about, unlike the previous ImageNet era or the, ImageNet object recognition era, there's so many other ways to improve the model performance other than just fine-tuning. So many of them are actually ordered by the difficulty or the involvement of human labor. You can think of the fine-tuning by collecting a lot of demonstrations has the highest involvement of human labor, right? You have to go out, collect a large data set, label them perfectly, hopefully have a few data annotators to double check there's no mistakes, and then you train a model. Very time consuming. Now with large language models, you can just show 2 demonstrations. And all of a sudden the model is able to follow your instruction and perform new tasks. And that only takes maybe 20 minutes of your time. And sometimes for a task that you do not know how to solve, you can simply describe it in words. So you can solve a new task within a few seconds. So the key observation we made in the APE project or the automatic prompt engineering project is to notice that if the model can leverage both the demonstration and task description, we can form a self-improving loop with almost no human involvement or human labor. That is, we can start with a demonstration and ask the large language model to come with a task description. And now given the task description, the initial task description guessed by the model, we can iteratively improve on it. And in the end, to do better on the actual training set. So in the large language model era, once we obtain an artifact, that is, once we obtain an API access or an open source large language model, the bar of entrance to improve these models has been significantly lowered, because now we can actually form a self-improving loop of these models to continue to do better on a given task with no human involvement. And all the data can be generated by the model themselves. So moving forward, so what does this intuition tell us? What does this takeaway tell us? So to continue to improve the performance of large language model in academia or in places where there's not a lot of compute, the key question to answer here is to think about, how do we channel more human flops or more human labels to the problem? And how can we create better demonstrations and leverage the existing performance of our model to create or to refine those demonstrations, to refine the task descriptions iteratively so we can actually have a self-improving loop. So the closing thought here is that because the barrier of entrance to improve large language model is so much lower than the previous image recognition models, the ImageNet models, you don't have to collect tens of thousands of examples anymore. All you need is just sit there and think really hard about what task you would like to solve and write down the instructions. Then you can run the model to gradually and self-iteratively improve its own instruction. And I believe it's a bit hard to think the performance of these systems is going to taper off because of the self-improving property. And in fact, the model and the overall performance of this system may still improve over the years, even though the architecture and the algorithm of training these models may be stale. That is, even if we stay in the current paradigm and continue by training larger and larger GPT models, because the barrier of entry is so low for everyone to jump on a model that can follow instructions, the open source community, the academic community can continue to improve the model performance just by simply prompt the model better and then connect the model in a self-improving way. So in the end, I'm going to leave everyone with this particular curve. So depending on your time scale, if you just zoom out, if you squint your eyes and zoom out, I think there's always the next exponential curve that's waiting to be taken off. And any one of you has opportunity to discover these new technologies, just hidden behind the most popular topics. And you never know that in the next 10 years, we may have entirely new technology that will take off and perform so much better than the current paradigm. Well, thanks everyone for the talk.
Thank you, Jimmy, for the excellent lecture. I believe there are already some questions in the chat box, and the session is now open for questions from the participants. You can unmute yourself and ask.
Yeah, great. So there's a question in the chat. So please explain the intuition or reasons of performance by self-promoting or self-improvement. Yeah, so let's think about there's two sources of improvement for the particular task I described. Let's describe the one that's easiest to understand. Let's look at this particular example, right? So the way how ape works is that you're given a particular training set, and the goal is that I would like to guess the best instruction to describe this training set. And now the way we evaluate it is that condition on this generated instruction, how well does the model score on each of the examples in the training? And then you can average the evaluation metric. In this case, we use log likelihood. Each of the generated instruction, and then we can sort them by the likelihood value. So clearly, you can imagine in the first step, we're able to immediately improve the model performance on this data set. Now we have better instructions to describe the task. So now how do we improve on top of this? We can take the top K best performing instruction, and we can leverage the model's language understanding capability, say, hey, these are really good instructions. Can you tell me a few more that has a similar semantic meaning, but very different? So now in this resampling steps, the model is going to often propose a few more instructions that's similar to your best performing ones. Think about this as like evolutionary search. You start with your best candidates, and then you mutate your best candidates a little bit. You do a little random walk around your best candidates. The hope is that the best performing sentences can actually be discovered through this random walk process, right? So then you can just form this self-improving loop. But eventually, the performance will probably plateau, right? And that purely depends on, the underlying, how well the model can follow instructions and how strong your base model is. So in this example, we use a Copilot model from OpenAI. So that's essentially, how the loop works. We start with the data set, and then we ask the model to first generate a set of instructions. And then we score each of the instructions. We take the best K instruction. We ask the model, hey, can you generate a few more? Once you generate a few more, you can say, hey, how can we improve these continuously through step 4 and 5 to form this loop. So this is the simplest form of self-improvement. And then, so the second source of self-improvement actually comes from leveraging the human knowledge to kind of like take a sneak peek of the psychology of this model. So what I mean by psychology of this model is that there's a lot of human priors in terms of how to improve the instructions. For example, in this image generation task, right? The initial instruction is that generating a very beautiful painting of a mountain next to waterfall. So that's your initial instruction. And to a human, the way to continue to improve this instruction can simply just be like, well, instead of a beautiful painting, what happens if you generate a very beautiful painting or very, very beautiful painting or very, 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 very beautiful, right? So you can actually describe the task just by simply saying, the intuitions here is like, you can literally tell the model, do the task better. And the model is actually be able to carry out this task and just perform slightly better on the evaluation metric if you instruct the model to do so, right? Why is that? So this part comes from these models are actually trained to imitate human, right? So there's a lot of understanding of the world, of our knowledge, in terms of, what someone means when they say write a very good essay versus write a very bad essay. Any of those adjective modifiers, actually the model internally does have some understanding of, well, when we say good, that means mediocre. When we say very good, that means we actually need to try really hard to perform at the highest quality. So once these models are trained on those human language, understand this basic concept, then it's not too hard to understand that once we ask the model, hey, you can actually come with new instructions by saying that just perform this task better, the model is, we can leverage these sort of human priors. So again, right? So two sources of improvement. The first source of improvement comes from we have a particular training set. We can do evolutionary search to improve on top of the training set and hope this generalizes on the test domain. So this is very similar to the traditional machine learning, except for we'll perform in instruction space. And the second source of improvement comes from the language understanding of the LLMs and understands that when someone says perform a very beautiful painting or perform a very careful calculation, the model understands that it needs to be accurate. So I hope this can answer your question.
Yeah, thank you for such a detailed answer. Any other question from the participants, please? Any other question, participants? Session is now open for you. Maybe I wanted to just ask, expect some comments from you about, let's say, what do you think about the explainability? for large language models, especially when they are doing some specific kind of behavior against some prompt engineering. I mean, is it possible to add explainability on top of them?
Yes, I believe so. So in fact, because we train this language model to imitate human behavior and to complete a sentence or complete patterns, explainability is quite easy to be incorporated, right? So the easiest form of explainability is the form of chain of thoughts. That's what I'm showing here from Joe and all and the Google group here. So in the traditional NLP models, where you're given a question and model need to pick one of the four choices, right? And then we evaluate the performance of the model based on which choice they pick. So they operate more or less like a black box. But in the age of large language model, we can prompt the model to give the particular form of answers we want, including the answer with the explanation, right? You can think of the reasoning chain or the chain of thoughts here is a form of explanation of how the model
Yeah.
actually reached the final
No,
answer.
but this is mainly true for text-only LLMs, right? What about what is your opinion about, let's say, multimodal LLMs like MedPalm 2 or GPT-4, etc.?
Yes. So I believe this exact same process is very much applicable to the multimodal model.
Okay.
So in the next few months, I believe that you will see far more powerful open sourced uh, multimodal VLMs
Mhm.
and also VLM APIs that are released by different labs, different organizations. And once we obtain these models, we can apply the same chain of thoughts or the visual chain of thoughts prompting techniques, right? We can say, hey, here's a particular X-ray diagnosis image. As a, you know, uh, as a radiologist, this is my initial assessment of this particular CT scan. So the human can generate a few, like just maybe one or two these chain of thought promptings for a particular CT scan. And then in the test time, when you present a new CT scan, these VLMs will also be able to follow the exact same output format and trying their best to explain its reasoning path on, whether there's a particular cancer on the CT scan. So in other words, incorporating explanations is the same as incorporating these chain of thoughts. And
Yeah.
don't get me wrong, sometimes the chain of thoughts or the explanations uh can be pretty off, can be, can contain hallucinations even, right? For a lot of us who played with GPT-4V, when we use them to detect traffic lights, the model is not particularly very good at those tasks. Um, but as the model improves over time, and as um, these models get longer and longer contexts, allow us to fit in more and more few shot examples, I believe the performance of these systems is actually going to improve in terms of their explainability. And in fact, you can, write down a few of those medical diagnosis reports with a real human doctor reading a CT scans, uh, and then you can ask the model to generate a few different output from a test CT scan, and then you can try to average the diagnosis or take the majority
No, I
uh,
see. Yeah.
of the diagnosis.
Yeah.
Thank you. Professor Das, can I ask one question?
Yeah, please go ahead.
Professor, how this or how are these models expected to evolve, say, in predicting of stock market performance? I mean, there's a lot of data that it's collecting, but right now it doesn't give any good predictions. But do you think they will attempt any of that, or they
Yeah,
can do
that's
a
an
good job at
excellent.
that?
Yeah, that's an excellent question. So I have not personally worked on the stock market data. But if we look at a lot of the training examples on the internet, right, or the traditional time series prediction models, so what happens in those domains is that you're given a sequence of numbers or sequence of features in time. And the idea is to predict, given these sequence of features that evolved in time, trying to predict whether the signal is going to go up or down in the future. It's oftentimes the informations are very coarse in these time sequences, right? So what I mean by that is, think about LLMs as a human intern, right? That you hired to solve your, financial prediction tasks. And this intern have never ever worked with financial data before. Simply feeding this intern this string of numbers and trying to predict up and downs will almost be impossible, right? So you can put this intern sit there, look through your books for 2 months, and very unlikely they're actually going to make a very accurate prediction. So now how can we make this system better? Again, going back to how would you train an intern to do financial analysis that you never, this intern have no prior financial background? Well, you will introduce them to some search engines to get additional market data. You will introduce them to different explanations from your previous colleagues who are very good at, financial analysts to explain the problem, right? So we actually need to get a few of those chain of thoughts reasoning paths as a few shot prompting examples. Now, given these few shot prompts, the models may have a chance to give you a pretty reasonable prediction. Right? So simply feeding a sequence of numbers to these models is unlikely to be successful. So that's my thoughts.
Thank you.
I think there is one last question on the chat from Nitin, and then we can.
Yeah. So Nitin is asking again on please advise on how one can avoid and minimize hallucinations. One understanding is use chain of thoughts prompting. So that's a great question. How do we minimize hallucination? So in fact, the hallucination capabilities of these models are the staple feature of why large language models are very good, right? So they are trained to complete the patterns to the best ability they can. And sometimes innately they may not have the capability to do so. And that's where the hallucination come from, right? So it all comes from, in the post-training phase, right? So there are a few of the techniques. Some of them have been released by Anthropic around a year ago. It's called the large language model largely knows what they don't know, right? So as the model outputting this particular reasoning chain, you can also ask the model to score itself, right? So it's very similar to how it does it in the automatic prompt engineer. So instead of scoring each of the example generated by the models using log likelihood, and then training set like what we did here, one can generate a few of these examples for each of the task. We take the majority voting, or we can just simply ask the model, what's your confidence level? Or is this statement factual? And we take an ensemble approach to that. So that will actually give you a pretty reasonable uncertainty calibration on each model's generation. Most time we don't do this in practice because it's quite expensive, right? For each generation, that means we have to generate a few different reasoning paths and we have to score them separately. So that can be very quickly be very expensive. And then, so fundamentally, you want to think about, well, maybe it is possible to train a model to say, I don't know, right? So if we think about how we train those large language models, they all train, in a pre-training phase to predict the next word in a sentence. And then once these models are very good at completing patterns, then trained trying to answer the question to the best ability they can, right? So oftentimes the training data is a form of the human instructions and then the best answer the human can give. Very few of those examples actually contain I don't know, right? So that's where the improvement can come from. So if anyone can identify what the model actually knows and what model doesn't know, and for the aspects that model doesn't know, generated the training examples to say, I don't know how to answer this question, right? Then maybe in the test time, the model is able to, have a more accurate responses than trying its best to answer all questions, right? So I think it's really just have to do with the way we train these large language model these days. The way we train them is almost treating the large language model as an oracle and feeding all type of tasks that we think an AI system should be able to solve. But there's always going to be a gap between what we think the system can solve and the base capability of those large language model, right? Depends on how much compute you spend, a smaller model simply would not be able to solve many complex tasks. And yet, we still train these small models trying to answer the question to the best ability, trying to answer the questions as good as humanly can. Then the result is that, well, the model just, gonna try its best, sometimes not give inaccurate answers.
Yep, I think that was great. And yeah, so thank you, Jimmy, for this excellent presentation. And if participants do not have any further questions, let us heartily express our gratitude towards the speaker for attending and delivering this nice lecture for our winter school on deep learning. I fervently hope that in some near future you will find time to visit India and visit the Indian Statistical Institute, which is a pioneering institute for research in statistics all over Asia, started in, I think, 1930s and then gradually evolving into its present shape. So thank you once again, Jimmy, and thank you all the participants for your kind attention. The session ends here.
Thanks, everyone. Bye.
Bye-bye. Have a good time.
Yeah, take care.